Welcome back to MindClash. I'm Alex, and today we're flipping the script. After Jankovici's intense reality check in episode 001, this episode is our optimistic counterweight. We're diving into the world of Amory Lovins, the physicist who has spent 50 years proving that energy efficiency isn't just a stopgap. It's a revolution. Lovins is the founder of the Rocky Mountain Institute and the man who coined the term Negawatt, energy that isn't used. He argues that by eliminating the 4/5 of energy wasted through poor design, we can phase out fossil fuels and nuclear power without inventing anything new and actually save money. It's a bold, systems-based vision that challenges conventional wisdom. To help us unpack this, I'm joined by Mark. Mark, you've gone through Lovins' 4 key talks, from his TED presentation on a 40-year plan to his RMI keynote. What was the first thing that really hit you when you started digging into his work? Did his optimism feel grounded, or was it something else entirely?
Thanks, Alex. What struck me immediately was the sheer scale of the inefficiency. Lovins points out that we're essentially throwing away 80% of our energy through suboptimal design. He frames the transition not as a technological hurdle, but as a business case. The idea that efficiency is 10 times cheaper than nuclear to avoid CO2 emissions was a real eye-opener for me. I was also fascinated by his concept of integrated design. It's not just about better light bulbs. It's about designing buildings and systems so effectively that heating or cooling becomes almost unnecessary. He cites the Empire State Building retrofit, which cut energy use by 70%. It shows that we already have the tools. We just need the will to implement them at scale.
Mark, let's dive into that core thesis. Lovins presents this famous stupid energy policy multiple-choice test where the options are oil wars, climate change, or nuclear holocaust. He claims there's a fifth option. Can you break down what that fifth option actually looks like in practice?
Exactly. The fifth option is essentially none of the above. It's about realizing that we don't need to choose between economic decline and environmental disaster. Lovins argues that by substituting imported fuels with efficiency, what he calls negawatts, we can avoid all those pitfalls while actually improving living standards.
That sounds almost too good to be true, but Lovins backs this up with some serious numbers, doesn't he? I remember him mentioning a massive financial figure regarding the cost of transition versus business as usual. What was that again?
Right. He claims that by 2050, this strategy would save $5 trillion compared to the business-as-usual scenario. Instead of spending that money on importing oil or building nuclear plants, we invest in efficiency. It's not just about saving the planet, it's a net positive for the economy.
$5 trillion saved. That's a staggering amount, and I know he uses the Empire State Building as a prime example of this potential. How did they manage to cut energy use so drastically without completely tearing the building down?
They didn't just swap out bulbs. They used integrated design. By improving the insulation, upgrading the windows, and optimizing the HVAC systems, they reduced energy consumption by 70%. Lovins argues this proves that we can retrofit existing infrastructure to be incredibly efficient without inventing new technologies.
So if the technology exists and it's profitable, why haven't we done this everywhere? Lovins mentions that the barriers aren't technical. If that's the case, what is he saying holds us back?
He explicitly states that the obstacles are cultural and institutional, not technical. He talks about acupuncturing the system to fix market distortions, like subsidies for fossil fuels. He believes that once we remove these political roadblocks, efficiency will naturally take over because it's cheaper.
It's interesting that he frames it as a choice between avoiding bad outcomes and gaining something positive. He even calls a negawatt the cheapest, cleanest, safest, fastest power plant. Do you buy that comparison?
From a pure efficiency standpoint, yes. Since a negawatt is energy you never have to generate, transmit, or distribute, it avoids all those losses. Lovins argues it's already built in the sense that the potential exists in our wasteful systems. It's the ultimate low-hanging fruit.
All right, let's zoom in on the actual playbook. Lovins breaks this down into 4 specific sectors: buildings, transport, electricity, and industry. It's a massive scope. How does he propose we tackle all 4 simultaneously without getting overwhelmed or needing some magical new invention?
The genius is that he doesn't rely on new inventions. He argues we just need to scale up existing technologies. For instance, in industry, he points out that industrial cogeneration, using waste heat for power, could displace 2/5 of U.S. coal electricity right now. It's about using what we already have smarter.
2/5 of coal electricity just by capturing waste heat. That's huge. But what about the historical precedent? Is there any evidence that we can actually sustain the kind of efficiency gains he's talking about, or is this just theoretical optimism?
It's definitely not theoretical. Historically, the U.S. has reduced its energy intensity by 2 to 4% per year already. In fact, China has achieved 5% annual reductions over 25 years. Lovins argues that stabilizing emissions only requires 2% per year, which is well within historical precedent.
5% in China is staggering. It really challenges the narrative that efficiency kills economic growth. Lovins frames this as doing more with less, but can you explain how that actually looks for the average consumer or business? Is it just about turning off lights?
Far beyond turning off lights, it's about integrated design. Think of buildings that don't even need traditional HVAC because of superior insulation and natural lighting, or vehicles that are lighter and more aerodynamic. It's about delivering the same service, comfort, mobility, with a fraction of the energy input.
So, if we combine these efficiencies across all 4 sectors, what's the end game? I know he's pretty bold about the timeline. When does he actually think we can eliminate U.S. oil use completely?
He's quite specific. Lovins projects that we can eliminate U.S. oil use entirely by the 2040. This isn't just about electric cars. It's about electrifying transport, using hydrogen for heavy industry, and switching heating systems from fossil fuels to electric heat pumps. It's a comprehensive systemic shift.
Eliminating oil by the 2040 is a very tight window, and you mentioned electricity earlier. How does the electricity sector fit into this? I assume it's not just about building more solar farms.
Correct. The electricity sector is transformed by reducing demand first. By making everything else more efficient, the load on the grid drops significantly. Then, the remaining demand is met by renewables and grid modernization. Lovins emphasizes that efficiency makes the renewable transition cheaper and faster.
It sounds like the core message is that we've been looking at this all wrong. Instead of focusing on supply, we should be focusing on waste. Does Lovins ever address the counter-argument that efficiency might just lead to more consumption overall?
He does, but he flips it. He argues that doing more with less means higher quality services for less cost. In the U.S. context, where energy use is already high, the focus is on eliminating waste, not reducing comfort. The data shows that economic growth and energy decoupling can happen simultaneously if we fix the design flaws.
So we've talked about the big picture, but let's zoom in on buildings. Lovins is famous for the concept of integrated design. What does that actually mean in practice? Is it just about adding more insulation, or is there a fundamental shift in how architects think?
It's a complete mindset shift. Integrated design means optimizing the entire system, not just individual components. Lovins argues that if you optimize the building envelope, insulation, windows, orientation, you can often eliminate the need for expensive heating and cooling equipment altogether. It's about making the machine unnecessary.
That sounds almost too good to be true. Eliminate the HVAC system entirely. And where is this actually happening? Is this just a niche experiment, or are we seeing real-world adoption at scale?
It's definitely real. Lovins points out that there are already over 40,000 passive buildings in Europe that operate without traditional heating or cooling. These structures maintain comfortable temperatures year-round through design alone, proving that the technology is mature and scalable.
40,000 is a significant number, but I'm more interested in the U.S. context. We have older, less efficient stock. Does Lovins have any examples of massive retrofits that show this works in existing buildings?
Absolutely. The Empire State Building retrofit is the classic case study. They didn't just swap out lights, they redesigned the entire envelope and systems. The result? A 70% reduction in energy use. It's a landmark example of how deep retrofits can transform iconic structures.
70% is dramatic, and I assume Rocky Mountain Institute practices what it preaches. Is their own headquarters a model for this integrated approach?
Yes, their new office is cited as one of the most energy-efficient buildings in North America. It's not just about being green. It's about creating a healthier, more productive workspace while consuming a fraction of the energy of a typical commercial building.
I read about some social housing projects in Amsterdam that take this even further. They're not just efficient, they're producing energy. How is that possible?
It's a powerful example of integrated design meeting policy. By combining superior building envelopes with on-site renewable generation, these social housing units actually produce more energy than they consume. It turns housing from a cost center into an energy asset. Lovins argues that the grid is already transforming. In Texas and California, massive solar combined with battery storage is increasingly running the grid. This decentralization, paired with efficiency, reduces the need for new fossil fuel plants entirely.
That shift away from centralized plants is huge. It brings us directly to Lovins' 1976 manifesto, Soft Energy Paths. He coined this term to describe a completely different approach. What exactly defines a soft energy path compared to the heavy industrial model we're used to?
It's about matching the quality of energy to the quality of the need. Soft energy means decentralized, renewable, and appropriable sources. Instead of massive, fragile megaprojects, it's about local solutions that communities can manage and maintain. It's energy that fits the scale of human need.
Decentralized and local, I like that. But let's talk about the elephant in the room, nuclear. In 1976, nuclear was the future. How did Lovins critique it back then, and does his argument hold up today?
Lovins argued then, and still argues now, that nuclear is simply too expensive and slow. He called it an old boys network of subsidies that relies on government backing rather than market viability. His data showed that nuclear was in relative decline even before renewables took off.
An old boys network. That's a strong phrase. But beyond the politics, what's the economic argument? Why is efficiency a better bet than building new power plants?
The math is staggering. Lovins demonstrated that saving energy is roughly 10 times cheaper than generating new nuclear power for every ton of CO2 avoided. A negawatt is the cheapest, cleanest, and safest power plant you can build, and it's already built inside our inefficient walls.
10 times cheaper. That's not just a marginal difference, that's a paradigm shift. If efficiency is so much better, why does the public still associate energy security with big power plants?
It's about resilience and perception. Lovins argued that microgrids and decentralized renewables offer superior resilience against disasters. When a hurricane hits, a centralized plant goes down, but local solar and batteries keep the lights on. It's security through diversity, not through giant targets.
Security through diversity. I see the appeal, especially with climate change increasing extreme weather events. But isn't there a risk in relying on supply chains for solar panels and batteries? How do we avoid trading one dependency for another?
That's a valid concern, though Lovins emphasizes that the material intensity of renewables is far lower than fossil fuels or nuclear over their life cycles. He advocates for acupuncturing the system, fixing specific market distortions like subsidies for oil, rather than accepting the status quo. It's about smart design, not just swapping fuels.
Let's pivot to the red lines. Lovins is famously confident in microgrids for resilience, but does this overlook the fragility of the supply chains behind them? I'm thinking about the global dependencies for lithium, cobalt, and copper that keep these decentralized systems running.
It's a fair critique. Lovins minimizes the extraction impacts, treating them as secondary to carbon reduction. He argues renewables have lower life cycle material intensity than fossil fuels, but he often sidesteps the social and environmental costs of mining critical minerals, assuming technology will solve those bottlenecks.
Speaking of technology, he's incredibly optimistic about AI and optical chips reducing energy demand. But with data centers consuming massive power today, isn't this a dangerous underestimation? How can we trust that innovation will outpace the exponential growth in compute needs?
Lovins bets on physical layer innovations, like optical computing, to bypass electronic heat limits. However, this relies on unproven scalability. He assumes efficiency gains in hardware will offset demand surges, but this ignores the current reality of data center energy spikes and material shortages for advanced manufacturing.
Another gap is the political reality. Lovins often says obstacles are cultural, not technical. But what about sovereign nations whose security is tied to fossil fuel control? Can acupuncturing market distortions really override deep geopolitical interests and subsidy structures?
He acknowledges political barriers, but attributes them largely to cultural inertia and poor policy design. This view disconnects local economic viability from global power dynamics. It underestimates how national sovereignty and entrenched energy interests can block even the most cost-effective solutions, regardless of their technical merit.
Then there's his applied hope framing. It empowers individuals and businesses to act, but isn't this a form of reductionism? By focusing on individual agency, does it inadvertently let structural power and systemic injustice off the hook?
Exactly. His technocratic optimism often bypasses radical critiques of power structures. While doing more with less is powerful, it can feel like a depoliticized narrative. It risks ignoring the redistributive justice issues inherent in a global energy transition, focusing instead on efficiency as a moral and economic imperative.
Let's test that resilience claim again. Lovins claims microgrids are safer than centralized plants. But in an era of cyber warfare, aren't we just swapping physical vulnerability for digital exposure? A hacked microgrid could be just as catastrophic.
Lovins doesn't fully address the cyber risk of digital infrastructure. He assumes that decentralization inherently reduces attack surfaces, but interconnected smart grids introduce new vulnerabilities. The reliance on software for management might actually increase systemic risk in ways he hasn't adequately quantified.
This brings us to our first open question for EP003. If obstacles are cultural and political, how does the RMI propose to overcome the resistance of nation-states whose security is still tied to fossil fuel control? Can market acupuncture work against hard power?
And our second, how do we reconcile the promise of no new inventions with the urgent need for scalable storage and transport tech that doesn't yet exist at competitive cost? We can't ignore the material reality of supply chains if we claim to be practitioners, not theorists.
Mark, we've really dug into the gaps. So, what's your final verdict on Amory Lovins? Is his fifth option still viable, or has his optimism outpaced political reality?
He's a brilliant system thinker who proved efficiency is cheaper than fuel. But his belief that obstacles are cultural underestimates hard geopolitics. I'm left wanting more rigor on the global power dynamics he glosses over.
That tension is exactly what we're unpacking next. In EP003, it's Jancovici vs. Lovins. 3 voices, 2 visions, 1 hour of head-to-head debate. Don't miss it. If you enjoyed this deep dive, please subscribe and leave a review. It helps us reach more curious minds. I'm Alex, this is MindClash. See you in the next one.